Okay, so section 2.1 is kind of an introduction to trigonometry. And we in the past we've kind of thought of angles as being an angle in a triangle or a polygon or something like that. Okay, we've usually studied them in the context of triangles, and now we're going to look at angles in a different way. Okay, your book says in geometry an angle is formed by two rays with a common endpoint, and in trigonometry we often consider angles to be rotations of a ray. Okay, so we would say that an angle would be the initial position of a ray, and then that ray would rotate, and then you end up with a terminal arm. Okay, so initial arm or side, sometimes called the side, and the terminal side, right? And then you can have that angle of rotation. Okay, so angles that are in standard position have two qualifiers. Okay, the vertex has to be at the origin. That's one thing. And the other thing is that the initial arm is on the positive x-axis. Okay, so we'll just look at these ones here. They're, I think, quite similar to the ones in your book, and I just put them up here so I don't have to keep drawing the pictures. And so to decide whether an angle is in standard position, you just need to make sure that those two things are true. Okay, so for example, this one here, you can see that its vertex is at the origin. Okay, but here's its initial arm. That's not on the positive x-axis, so that's going to be a no as far as being in standard position goes. If you look at this angle, you can see that its vertex is at the origin and its initial arm is on the positive x-axis, which makes it a yes. In this angle, neither of those two things are true. Okay, here's the initial arm. It's not on the positive x-axis. Here's the vertex. It's not on the origin. Okay, so I'm going to say no. Look at this angle. Even though this angle here is greater than 180 degrees, okay, so a bigger angle than we'd usually even look at in previous geometry courses, it does have its initial arm on the positive x-axis and its vertex is at the origin. Okay, so this is a standard position angle. Okay, as is this one. Okay, the vertex is at the origin, the initial arm is on the positive x-axis. Okay, going pretty well so far, I think. Here we have our vertex on the origin. Initial arm is on the positive x-axis, even though I kind of made it look like it wasn't. Yeah, there it is right there. So this is a yes. This one here, the vertex is not on the origin. Yes, the initial arm is on the positive x-axis, but the vertex is not on the origin, so that would be a no. Both things have to be true. And here you have an angle. It's in the first quadrant. Its vertex is not on the origin, and its initial arm is not on the positive x-axis. So basically, just ask yourself those two things to find out whether an angle is in standard position. Okay? That's kind of explained on page 75, I guess. Page 77, angles in standard position. I don't know if you're familiar with the quadrants, so we'll just look at them really quickly. Okay, this is quadrant 1 right here. Okay. And in quadrant 1, you have angles that are between 0 and 90 degrees. Okay, not including those because those aren't actually in the quadrants. They're on the axes. Okay, those are called quadrantal angles. So a standard position angle with both its initial and terminal arm, right? They'd just be overlapping because there would be no rotation. You could have an angle of 0 degrees. Okay, if its terminal arm. Sorry, if its terminal arm was right there. Okay, you could have an angle of 90 degrees if its terminal arm was right on the positive y-axis. Okay, you could have an angle of 180 here or 270. Okay, so these are not included, okay, assuming that's the terminal arm. Okay, we're talking standard position angles. Okay, so those aren't included. So when you say between 0 and 90, okay, but not including. Okay, that would be in the first quadrant. In the second quadrant, you're going to have angles that are between 90 and 180. Okay, in the third quadrant, you'll have angles between 180 and 270. Okay, and in the fourth quadrant, I didn't write that, third quadrant. Fourth quadrant, you're going to have angles between 270 and 360. Okay, that's where your standard position angles will be. Okay, positive standard position angles between 0 and 360, because angles can be bigger than 360 because you can just keep rotating around there. And it doesn't really mention that in your book, but if you don't say that you're only looking at angles between 0 and 360, you could have an angle that's, say, 360, goes around once, and then it keeps going, say, 90 degrees more. Okay, and then you're going to have an angle of 450. So that's certainly possible. And there's also negative angles. And so you can just keep going up. But I don't think we're going to worry about that in this section. I don't see it coming up. Okay? All right, the next topic, so that's standard position angles. So that's an important topic. Okay? The next topic is reference angles. Okay? And we do want to put our angles in standard position, but sometimes we don't want to consider that whole angle. Sometimes we want to look at the reference angle. Okay, so what I have here is I've drawn an angle in quadrant 1, and I've got an angle in quadrant 3 over here, an angle in quadrant 2 here, and an angle in quadrant 4 here, okay? And so we're going to see where the reference angle is. And so if you look on page 78, it'll tell you that the reference angle is the acute angle whose vertex is the origin and whose arms are the terminal arm of the angle and the x-axis. See, but not the positive x-axis like a standard position angle. It would really be the nearest x-axis. Okay, so in quadrant 1, say you're going to have an angle right here. Okay, to find your reference angle, you want to have the angle between the terminal arm and the nearest x-axis, which happens to be the positive x-axis. So our angle and our reference angle are going to be the same thing in this case. Okay, so the angle is equal to the reference angle. Okay, so that's fine. That really doesn't teach you anything because it's not different from what you already knew. Okay, but and I mean, you could be looking at this. This is on page 78 as well if you want to read a little further on this. In the second quadrant, here's my angle. Okay, my angle is between, it's in standard position, so I've got my initial arm and my terminal arm here. And I just labeled them with I and T, but that's not really standard, so I won't leave it. But if you want to look at the reference angle, you have your terminal arm, and then you want the nearest, like the negative x-axis, because that's actually closer to it than the positive x-axis. So my reference angle is actually right here. Okay, and notice the reference angles then are always acute. Okay, so they're always between 0 and 90 degrees. How would you express the relationship between the two here? Well, you can probably see that in order to find, well, you can see that your angle and your reference angle here always are going to add up to a straight line if it's in the second quadrant. Okay, so you can pretty much say that your reference angle in the second quadrant is just going to be 180 degrees minus your angle. Okay, you're not going to do that very well. I guess you can probably do that in your head because I think, you know, I mean, people do it, but I haven't often seen somebody calculate that, I guess. Okay, in the third quadrant, here's my angle. Okay, and here's my reference angle. Okay, so this is theta. That'll be theta r. Okay, because the terminal arm is closest to the negative, closer to the negative x-axis than it is to the positive. All right, so how do we get our reference angle? Well, what you would do is you would take that whole big angle that we have right here, and then you would subtract 180 from it. Okay, so the reference angle would be the angle minus 180. Okay, so that's true in the third quadrant. So notice, in the first quadrant, they're the same. All right. In the second quadrant, it's going to be 180 minus the angle. In the third quadrant, it's going to be the angle minus 180. And maybe you can figure out on your own what it's going to be in the fourth quadrant. Okay, in the fourth quadrant, we're looking at an angle like this, but our reference angle is going to be here. Okay, so what you notice about that, hopefully, is that they're going to add up to 360, right? Because it just basically is the rest of the way around. And so your reference angle is just going to be 360 minus your angle. Okay? So that's basically reference angles. And okay. And then the last thing that we look at is the special right triangles. Okay, so I'll just draw some nice special right triangles out for you. Hopefully I can draw a good one. Okay, and we look at these right these special right triangles a fair bit. Okay, so you tend to want to memorize them. What I'm trying to draw here, sort of unsuccessfully. I wonder if there's a shape for that. Look at that. That looks like a nice triangle. You bet. Okay, that's the one I want. So I'm just gonna erase that, and I'm gonna make that one. Okay, now what I'm doing here is I want to make a triangle that has basically it's a right triangle, and the two sides are the same. Okay, the two sides that aren't the hypotenuse. All right, so it's two legs. So it's got a 90-degree angle, and I want to make sure those two sides are the same. And I'll just make them one. Okay, so if they're both the same, and you know that this is an isosceles triangle, okay, because those two sides are the same. That means that those base angles would be the same. Okay, and so this is actually referred to as a 45, 45, 90 triangle. You'll be happy to know there's only two special right triangles that you have to worry about. And this is pretty easy to figure out because the only thing we really need here to know is what the length of the hypotenuse is. Okay, so just using the Pythagorean theorem, c squared equals a squared plus b squared. So that'll be c, the hypotenuse. It's going to be 1 squared plus 1 squared, which is 1 plus 1, which is 2. And so that's always c squared. And then c is going to be root 2. And I'm not going to go plus or minus root 2 because it's a length, so I know it's going to be positive. Okay, so this is my special right triangle, or one of them anyway, my 30, 60, 90 triangle. Okay, and these are its measurements. Okay, so that's one important triangle, and we'll see what we use it for. It's really easy to determine the primary trig ratios for this because we have exact values for the sides. So for example, sine 45. Now just looking at this triangle, you don't have to put it in your calculator. You know sine is the opposite over the hypotenuse. Okay, so the sine here would be 1 over root 2. We always want to rationalize the denominator. And so that's going to be root 2 over 2. Okay, so we can use this to calculate exact values. So it's really, it's important to have the exact values here. If you look at that, cos 45 is also going to be equal to the same thing because the adjacent is also 1. So 1 over root 2 equals root 2 over 2. Okay, and tan of a 45-degree angle is opposite over adjacent. So opposite the 45-degree angle is a side with a length of 1. Adjacent to it is a side with a length of 1. So the tan of a 45-degree angle is 1. Okay, so that in a nutshell is the special right triangle, 45, 45, 90 triangle. Okay, I've got about 2 minutes to get through the next one, and then YouTube won't let me publish my video. So I'm going to go quick. This is going to be the 30, 60, 90 triangle. Okay, so I'm going to make it kind of like this. I'm going to do my best. Can't make any promises that it's going to be perfect, but that's okay. It's just a sketch. And when I write on there that that's a 30-degree angle, then that makes it true. Okay, 60, 30, 90. Okay. The way that they get this here is they show you that you can consider this to be half of an equilateral triangle. Okay. So if you take the equilateral triangle and you make each side 2, okay, and then you just cut it in half, this bisects this angle, making it 30. Okay, that makes this a 9. That makes this a 90-degree angle. Okay, so and this part here becomes 1. Okay, so this is 1, 2. If you use Pythagorean theorem, c squared equals a squared plus b squared, you're going to find that this is root 3. Okay, and so you can figure out the sine and cos and tan values just like you did before. Sine of a 60-degree angle, opposite over hypotenuse, root 3 over 2, and that's the exact value you're looking for. Okay, I got to shut this down because YouTube's not going to allow it to be posted if it's more than 15 minutes, so you can complete those ratios as an exercise if you like, and we'll look at the examples and it'll all be clear. Okay.